Hello everyone. Okay, this video I'm going to show you the terminology called potential energy. Okay, this is a section, a total. This is in energy conservation section. And in previous lecture, we show you the proof of the concept of what is conservative force, what the conservative force is. Okay, and conservative force is special. Okay, it can when we try to calculate the work done by the conservative force, we found it can sometimes release energy and also store the energy. Okay, and for the non-conservative force, it always dissipate energy. So conservative force is very special. And so from conservative force, okay, we will want to talk about this video is, so we now have a concept called conservative force. And right now we want to do is from conservative force, and we go to call the potential energy. Go to potential energy from conservative force to potential energy. Okay. I cannot move this. Can I move this? Ah. Yeah, I'm trying to. Yeah, I'm move this. Okay. So I want to introduce the potential energy. Potential energy, the term called potential energy. Okay, in fact, the potential energy is a term we human develop or we human define to reach the final to reach the to reach the final energy conservation concept. Okay, so potential energy is we human defined. Like I said, it's we human defined. We finally want to reach the conclusion energy conservation. E N E-N-E-R-G. So that's our goal. Energy conservation. Okay, energy conservation is our goal. It's our ultimate goal. We want to conserve. We want to reach the energy conservation. In order to reach this conclusion, we need to develop a new concept called potential energy. Okay, that's why that's potential energy comes from, because we want to get energy conservation. And energy conservation is very essential. Is essential to physics, because in every mechanical system, yeah, if you use energy conservation, it's much easier to solve the mechanical problems. Okay, you might say the mechanical problem can be solved. Yeah, mechanical problem seems to like mechanical problem can be solved by Newton's second law of motion. Yeah, of course, you can solve the mechanical system problem by Newton's second law of motion. But using Newton's second law of motion, yeah, you feel like use Newton's second law of motion. Sometimes sometimes it's not easy to solve. Okay, but but sometimes in the same mechanical problem, if you use energy conservation, it's much easier to solve. Okay, you will feel that because later we will show lots of example energy conservation problem, and you will feel like energy conservation problem is is easier to handle. Okay, it's unlike a Newton's law. It's very unlike a Newton's second law of motion. Newton's second law of motion, you have to do the force analysis, draw the free body diagram, and lots of vector calculation and analyzing each component of a vector, and then set up a lot of equations. Yeah, yes, it's difficult. I think you feel that. Okay, but later we will show energy conservation is really it's a very easy tool to solve the mechanical solve mechanical problem. And for in this class, right now we only have two potential energy we want to introduce. One is elastic potential, and the other is gravitational potential. Okay, so let's start with it. So how to get the potential energy? It's all, yeah, I think we demonstrate very similar example in last video. We just calculate calculate the work done by conservative force. Okay, so let's start with calculate. We are going to do the calculations is work done by conservative force. Conservative force. And I think we demonstrate something, demonstrate in the previous video. I'll demonstrate a very similar calculation previous video. Okay, let's start with the elastic force. Suppose I pull the spring from initial position xi to the final position xf. And also, yeah, the same pull at the constant velocity. Okay, pull at the constant velocity. Okay, since it's pull at constant velocity, that is no acceleration. So the acceleration, so the sigma f or net force is zero in the moving direction. So your F pull is equal to your F spring. Okay, and let's calculate the work from the F spring done by F spring. I think it's very similar because the elastic force is a variance force. Okay, elastic force is a variance force, so you have to use the integration to calculate the work. So let's do the integration xi xf, and F spring is, okay, first of all let's just write F spring and dx. Okay, and so okay, let's continue. Okay, F spring, so xi xf S spring is equal to minus kx dx. Okay, so elastic constant or force constant, yeah, it's a constant, so you can factor it out. And you will have very simple power function integration x dx. Yeah, I hope you can do the integration right now, because it's not really that difficult. So you will reach the conclusion here. Sorry, xi squared. Okay, and we did a little arrangement here. Let's just make everything look nice. Okay, kxf squared minus root xi squared. Okay, that's the first one. Okay, we calculate the force done by the spring. Oh, sorry, the work. Yeah, the work done by the spring force. You'll reach with this conclusion, and we define elastic potential energy. And in the potential energy in this course, we use the U. Okay, so we define as spring potential energy is 1/2 k times x squared, and x is compression value or stretch value, spring compression, compression value of spring or stretch value of spring, with respect to it's not, which is not proper term, or respect to equilibrium position, equilibrium position. Okay, that's x means. So x, yeah, if compress is negative value, is stretch is positive value. Okay, so the compression value and stretch value with respect to the equilibrium, the equilibrium position of the spring. Okay, and the stretch value or compression value square times the force constant and divided by 2. Let's call elastic or spring elastic potential energy. So so finally we will get the spring is equal to, let's say, minus u spring. So it's final state minus spring initial state. Okay, so that's spring potential energy. Yeah, elastic potential energy. Sorry. Okay, and we do the same thing on the gravitational force. Okay, the gravitational force, we do a similar thing. Yes, but we should use a little bit from here to here, okay, and move to here. Yeah, maybe I should move more. Ah, do it a little more. Okay, gravitation force do the same thing. Okay, right now we are pulling an object from the height hi to final height hf. And okay, gravitational force. We also calculate the work done by the conservative force and see. And we should see a similar situation happens. Okay, let's say W is gravitation. And okay, and okay, let's suppose this is y direction. Okay, this is y direction. Okay, and this is x direction. Okay, so let's do the work done by the gravitational force. So initial position of y to the final position of f, and the FG, and dy. Okay, and so what's the FG, the force, the gravitation force? Okay, let's suppose the mass is m. Okay, the mass is m, and acceleration acceleration of gravity or gravitation acceleration is g point down. So your Fg actually is point down, so it's negative. So the force is minus m times g and dy. Okay, so finally it's very integrated because mass is constant, gravitation, acceleration of gravitation is also constant, so we can factor it out, and we will just has this very simple integration. So actually, if nothing there, this means this is a 1. Okay, 1 dy, the integration is very easy. Okay, I hope you understand. Okay, so minus mg, so it will become yf minus yi. Okay, but yfy we right now is hf and hi. So actually, we will minus mg hf minus hi. Okay, and then we do a little arrangement. We do an arrangement. That's why we did it. That's similar to what we did on elastic potential calculation. Minus mg. Yeah. CHF and minus mghr. Yep. Okay. So we after we do the integration, we found okay, it's minus and some minus is a minus here in front of the bracket, and in the bracket there's a two terms subtraction of two terms, and then we just like what we did in spring elastic potential calculation. We define a gravitation potential. Gravitation is, we define is mass times acceleration times the height. H is the height. H. Okay, as we define, this called gravitational potential energy. Mass times gravity times height. That's the gravitational potential energy. So finally, we will reach this conclusion. If you find a work done by the gravitational force, gravitation and is equal to minus u, okay, gf minus u gravitational force initial state. Okay, that's the conclusion. Okay, so if you observe the left and right, you will find this a special pattern for the work done by a conservative force. And some book will say, okay, the work done by a conservative force can have this very simple, elegant conclusion. Okay, that's elegant conclusion. So the work done by a conservative force is equal to minus final potential energy, minus in bracket and final potential energy, and minus the initial potential energy, or just some just minus delta u. Okay. So the work done by conservative force is equal to the potential energy difference and times the negative sign. Okay. And this negative sign is very important because without this negative sign, we cannot reach the final conclusion. But final conclusion will be the next video. Okay. The final conclusion we want to reach is energy conservation. If we want to make the energy conservation formula work, and you must have the negative sign here. You must have the negative sign. If you don't have negative sign here, you won't reach the energy conservation conclusion. Okay, so the potential energy just what I said, it's a concept we human develop or devise for to reach energy conservation. Okay, okay, because energy conservation is much easy to analyze this and much easier for calculation in mechanical system. Okay, so that's the conclusion in this video I want to make. Okay, the work done by conservative force is equal to the potential energy difference times the minus sign. And in this class, we only have two potential energy. One is elastic potential energy, the other is gravitational potential energy. And elastic potential energy is 1 over 2 times force constant in times the compression value or stretch value with respect to the equilibrium position in square. Okay. And for the gravitational potential energy is mass times the acceleration of gravitation and times the height. Okay. Okay. So that's the potential energy we will face in this semester. Okay. And maybe next semester you have more potential energy, electric potential energy, and maybe next semester. Okay. So this is a video I want to introduce today. Okay, potential energy. Okay. For calculate the work done by a conservative force, we can get a define potential energy. And then in the next video we will reach energy conservation. Okay. So here's the video. I hope you can more understand the potential energy. Okay. So I'll start video here and see you in another video. Bye bye. Mhm. Hmm.